Nuclear power. Let's start first with how a nuclear power plant works. Remember, to generate electricity, you need to move a magnet in a coil of wires to create electricity. And so in a nuclear power plant, what happens is a process called fission, F-I-S-S-I-O-N, produces a lot of energy, a lot of heat. That heat heats the water to make steam, to move a magnet in a coil of wires to create electricity. In the United States, almost 20% of our electricity comes from nuclear power. So we use this quite a bit already in the United States. Problems with coal. We've already talked about big problem with coal is combustion. So I get my carbon dioxide linked to global warming. I also get mercury, toxic NOx with acid rain, and some radioactive components. In a nuclear power plant, big advantage is there's no burning, there's no combustion. In the reactor, in the core, are the fuel rods. If you look back for a second, those other neutrons being released go and hit another uranium atom and cause fission to occur, and that's the chain reaction. That's what this picture here is showing, that keeps the fission going. This is a good thing, and it also can be a problem, which we'll talk about later. So in a nuclear power plant, the fission is splitting an atom, produces a lot of heat. That heat heats up the water to turn it into steam. The steam moves a magnet in a coil of wires to generate electricity. Parts of a nuclear power plant. The two key parts are the fuel rods. The fuel rods are about 2 to 4% uranium-235. That is the fuel. Again, it is not burned. Fuel in the fuel rods undergoes fission. The other key component is the control rods. The control rods control the rate of the reaction by absorbing neutrons. So you block those neutrons and you control the rate of the reaction. This other thing about different parts is a moderator and a generator. Generator is where you generate electricity. Otherwise, a moderator is not important. Cooling system. The key idea of the cooling system is this is non-radioactive water vapor. It's just water vapor. Okay. In fact, we'll look later at how it works, and again, that it's not radioactive water vapor that's released. Advantages of nuclear power. It's the most viable alternative electricity source. What does that mean? It means it works now. It works if it's windy or not windy. It works day and night. It works if you're by a river or if you have high tides or low tides, or it works all the time. So it's the most viable. It works. In fact, about 20% of our electricity comes from it. Additionally, there's no combustion, no burning, so I can link that to acid rain, mercury, global warming. A second advantage, so again, we're on advantages and disadvantages of nuclear power. A second advantage of nuclear power is a lot of energy is released. And when I say a lot of energy is released, it means 1 gram of pure uranium-235 would release about 23,000 kilowatt hours. This is enough electricity to power my family's home for about 2 years. And this is what's contained in 1 gram of uranium-235 when it undergoes fission. Compare this for coal. I would have to burn over 3 tons of coal to get that same amount of energy. So huge amounts of energy released from the process of fission. Another advantage, a political and economic advantage, is that there are uranium deposits that are in the U.S. and our allies. Okay. Also, the seawater contains about 3 parts per billion uranium, so potentially it's not economically viable right now, but potentially we could get uranium also from the seawater. So we're not dependent on foreign countries that don't like us very much for this fuel source. So that's another advantage. The facilities are also tested and safe. If you click on this YouTube video, you'll actually see where they crashed an airplane into a test facility. Was not containing nuclear fuel, but basically to see if the containment vessel worked. And what we discovered is in the U.S., yes, it worked. Our containment is safe, and they tested it a lot. And again, as we said, it's the most viable alternative electricity source. So here's our recap of advantages of nuclear power, and there are several. Now, disadvantages. Your first disadvantage of nuclear power is NIMBY. As you know, not in my backyard. No one wants to live by a nuclear power plant. Not a big selling point for a home. Another disadvantage is plant accidents. We're going to talk about 3 of them a little bit here. And you'll notice there's the movie The China Syndrome. The China Syndrome was a movie that basically made people think nuclear power was this big conspiracy and this big accident waiting to happen. So this was a Hollywood movie, starred Jane Fonda, and this movie was in theaters when 3 Mile Island happened. It was released less than 2 weeks before the accident happened. So what happened as a result of this movie and 3 Mile Island is people freaked out and decided we did not want nuclear power plants in the U.S. They must not be safe. There must be this big conspiracy. And so we passed a moratorium on nuclear power plants. Moratorium, M-O-R-T-O-R-I-U-M. And M-O-R-A-T-O-R-I-U-M, a moratorium. And basically we didn't want more nuclear power plants because we were very afraid. So that ended up being another consequence of it, is we were very afraid of nuclear power in the U.S. In 1986, the biggest nuclear accident occurred, and this happened at Chernobyl in the former Soviet Union. Now, this was during the Cold War. The Cold War was a time when the Soviet Union and the United States had enough nuclear warheads to blow up the world several times. And so you didn't really want to start a war because it wouldn't end well. But what happened is there was a lot of battles going on in terms of posturing, in terms of trying to look better. So the United States would test a nuclear weapon. The Soviet Union would test a nuclear weapon. And this was kind of going back and forth. The Soviet Union was having trouble producing enough electricity. And so what happened is the powers that be in the Soviet Union wanted more electricity to be generated from the Chernobyl nuclear power plant. The operators were operating at max capacity, so they didn't think they could get more, but they were told to get more. So they ran a test where they raised the control rods more than safety design was supposed to allow. They raised those control rods a little bit more than they should have, and then what happened, it's called it flashed. The cooling water flashed and instantly turned to steam, and it was a steam explosion. It was not a nuclear explosion. I repeat, big idea here. Chernobyl was not a nuclear explosion. In fact, a nuclear power plant cannot explode like a nuclear bomb. It is not possible because there is not enough uranium-235 in it. This video, if you want to click on it, kind of shows Chernobyl, and it's very anti-nuclear power, but it kind of shows some images and things of Chernobyl. You look at this diagram, basically what happened is in this pink area around the reactor, that was water, okay? And that water would draw the heat away from the fission process, and that heat would go to the steam generator, or that really, really, really hot water would go to the steam generator, and the heat from that would boil water to produce steam to move a magnet and the coil wires to generate electricity. Again, notice on this picture the cooling tower. Water from the cooling tower never touches the core, so that's why we can say, despite what The Simpsons says, that the water released from the cooling tower is not radioactive. Back to Chernobyl. So what happened at Chernobyl is the area around the reactor, that pink area, that was water under extremely high pressure. Like, we're at 1 atmosphere of pressure, it's at like 1,000 atmospheres or something like that. I don't know the exact number, but a very, very high pressure, so it stays in the liquid form. What happened though is it flashed. It turned from liquid to steam and caused a steam explosion. And that steam explosion blew the top off the containment structure and blew nuclear debris hundreds of miles away. Pieces of fuel rod blew hundreds of miles away. This is the the Chernobyl exclusion zone. And if you can look and see on here, this is the scale of like 100 miles. So you can notice here, there is several hundred square miles that basically no one can live in anymore because of this accident. The Chernobyl exclusion zone is huge because fuel rods have been just sprayed all over the surrounding area. There's high levels of radiation from some of these areas. So huge amounts of radiation released from Chernobyl. So this was a very bad plant accident from nuclear power. Third accident is Fukushima. This was happened about in 2011, and what happened is there was an earthquake off the coast of Japan. That earthquake, everything worked perfectly. The nuclear power plant shut down like it was supposed to. The problem was this earthquake triggered a tsunami. That tsunami then flooded the generators. And what happened then is you lost power and all the backup power to keep the cooling happening of the reactor. So parts of the reactor melted down. Additionally, the spent fuel rods are kept in a separate area by the power plant, and those spent fuel rods are in these cooling pools. The water leaked from some of these spent fuel rod pools, and they ended up using seawater to cool them. The result from Fukushima is the radiation release is about 1/10 of that from Chernobyl. There are no reported deaths to date, and it's going to take decades to decontaminate the area around it. Basically, Japan now is not very pro-nuclear and is not going to do nuclear because of this accident. And a lot of radioactivity leaks into the ocean. Now, disadvantages of nuclear power. This is put a big star by this one because this is what most experts would say is the biggest disadvantage of nuclear power. So long-term storage and disposal of high-level radioactive waste. There are two types of two types of radioactive waste. There's high-level and low-level. High-level is the spent fuel rods. So basically what happens is a fuel rod contains the uranium-235. It's about 2 to 4% uranium-235. And the fuel rods are pulled out, when they're pulled out of the core, they have to go and sit in they have to go and cool down. These fuel rods then have to be disposed of somewhere. They're still going to be radioactive for at least 10,000 years. Low-level waste is basically like protective clothing that workers wear when they're around the nuclear power plant. Low-level radioactive waste is probably not even very radioactive. However, they still must deal with it. They still must dispose of it. And basically, they can dispose of it by storing it on site and dispose of it as ordinary trash, or there are some disposal sites as shown here, some special landfills. Sometimes they just dig a trench on the site, put it in containers, and bury it. So the low-level radioactive waste is not a problem. The big issue is the high level. What the current procedure is for high-level radioactive waste is to store it on site for 20 years to cool down. So basically it sits in these spent fuel rod pools, and in these pools it will cool down and sits there for 20 years. This was the big problem with Fukushima, is all the water drained out of these pools, and again there was problems that these rods were starting to melt. So that's why they had to spray seawater into these spent fuel rod pools to try to keep these rods cool. Then after these rods have cooled for at least 20 years, the idea is to kind of solidify them a little bit and then send them to mine geologic disposal, or Yucca Mountain, which is basically bury them deep under a mountain. Yucca Mountain is in Nevada, and that was the plan the U.S. was going to follow. When President Obama was elected for his first term, he cut funding to Yucca Mountain. So currently there is no plan in the U.S. for disposal, long-term disposal. We're storing it on site, and we don't have another plan at this point. Other options. Sometimes they talk, well, what else could we do with it? One option is just leave it at the current storage site. Again, there's concerns of securing it, but that is a potential option, and really that's kind of what we're doing at this point. Some concerns are, or some thoughts are bury it on the ocean floor, to dump it in these deep ocean trenches. Again, we don't know what's down there and what the impact that could have on the entire ocean ecosystem. Some said we could put it in the polar ice sheets, so those are big, we could just put it in there. Again, I don't know if that's a really good idea in terms of melting the ice sheets, but that has been a suggestion. Some say we could blast it into outer space. Problem with that is it's very expensive to send things into outer space, and the other issue with sending it into outer space is if it explodes, like this video would show of the 1986 Space Shuttle Challenger explosion. If it explodes when going up into outer space, you have now radioactive debris littered throughout the atmosphere. So that would be very bad. Reprocessing. This is what Japan has done, is they actually reprocess their nuclear waste to reduce it. And I'll explain that more in just a second. Or again, what the U.S. is doing is placing it, or wants to do, is place it deep underground in a geologic repository. Dig basically like mines, like a subsurface mine that goes a mile deep under a really dry mountain somewhere like Nevada, and then fill it in there and then basically seal it with concrete. And the hope is that the containment will last for at least 10,000 years. This is reprocessing. This is what Japan has done. And basically in the U.S., if you look at this picture, we're starting with the uranium mine. We mine the uranium ore, we process it, we enrich it to get to about 2 to 4% uranium-235, concentrate it, and then we go to a nuclear power plant. And then in the U.S., we just basically, when we're done at the nuclear power plant, we store it and we have to dispose of it. In Japan, they take the spent fuel, it goes to a conversion plant, is reprocessed and made into fuel again. So they get more use out of it because there still is some viable uranium-235 in the fuel rod. The problem, though, is plutonium. When you use reprocessing, you end up concentrating more amounts of plutonium. And plutonium is believed to be one of the most toxic substances known to man, if not the most toxic substance known to man. So by concentrating the plutonium, this was one of the concerns at Fukushima, is they actually had some of the spent fuel rods had higher levels of plutonium in them. And so this is one of the reasons the U.S. chose not to do reprocessing. It's very energy intensive, very expensive. So we just dispose of our spent fuel rods. In Japan, they did the route of reprocessing. So in the U.S., basically, we're going to take our high-level radioactive waste, store it on site for 20 years to let it to cool in these spent fuel rod tables, or the spent fuel rod pools, and then it's someday, maybe, going to go to Yucca Mountain or some other mine geologic disposal. And this image kind of shows you how they think Yucca Mountain will work. Again, it's stored on site now because no one wants it, and no one wants the waste to go through their state. This video is a good clip on some disadvantages of nuclear power and why some people are not big fans of Yucca Mountain and using it for the repository, again, the long-term storage of high-level, key idea, high-level radioactive waste. Transportation of the high-level radioactive waste. We have to transport it through populated areas. Typically it's transported by rail car, and so it's transported often through populated areas. So this is a disadvantage of it. You can look at the map of the U.S. Lots of major railroads here coming through the Chicago area. So a lot of nuclear reactors. If you look in the upper corner here, these nuclear reactors, lots of them out east. And again, we want to send all this waste out to Nevada. So much of it's going to come through Salt Lake City. It's going to come through the Chicago area. So you're going to send this nuclear waste through populated areas. What if a train derails? Has the technology to enrich uranium for power, then they can also do this for weapons. So uranium, when we naturally get it out of the ground, it's about 99.3% uranium-238 and about 0.7% uranium-235. A nuclear power plant has uranium-235 concentrated to a level of about 3 to 5%. Enriching uranium, that's what it's called, to get the uranium, to separate out the uranium-235 and to concentrate it to about a 3 to 5% concentration. That's called enriching uranium. Enriching uranium takes a lot of energy. It's a big, big process. This is our concern with Iran. Iran says we just want a nuclear power plant. However, the concern with Iran is once you can concentrate uranium to 3 to 5%, all you have to do is keep doing that again and again and again, and you can concentrate it to 90%. 90% uranium-235 is what is used in nuclear weapons. That's our concern with Iran. That's why we want to, and the UN wants to inspect their nuclear facilities to make sure they're not enriching beyond 3 to 5%. This is also why a nuclear power plant cannot explode like a nuclear bomb, because a nuclear power plant does not have a high enough concentration of uranium-235. So recap of the disadvantages of nuclear power is NIMBY. The biggest one most experts agree with is the long-term storage of and disposal of high-level radioactive waste, the transportation of the high-level radioactive waste to this permanent disposal facility. Now Yucca Mountain maybe, but it's closed right now, and the risk of accidents, Chernobyl in '86, 3 Mile Island in 1979, and now we can add on Fukushima is our most recent one in 2011. But again, long-term disposal of high-level radioactive waste is our biggest disadvantage according to the experts. Risk of dirty bombs and terrorism, and again, nuclear power plant technology. Enrichment is the same for developing nuclear weapons. So a disadvantage of nuclear power in a country, so letting any country of the world develop nuclear power as an alternative electricity generating source, is that once you have the technology to create nuclear power, you can just continue doing that process and you'll have a nuclear weapon.